Welcome to Part 2, Lecture 2, Study Design. So we're going to talk a little bit about study design and how it can affect your statistics. So we'll start off by comparing means between 4 groups. So as you remember, if you only have 2 groups, a t-test is perfect. If you have more than 2 groups, then you're going to be looking to use PRECEEDING or General Linear Model. So we're going to review the comparison of 2 means. We're going to look at the different layout of treatments, a one-way and a 2x2 factorial. And then we're going to have the allocation of treatments in a completely randomized design, a randomized block design. We've seen both of these to date. And finally, the split plot design. Let's set the scene. A study was designed to investigate the effect of target color and preceding exercise on reaction time. We had 24 students. That a target would appear on their computer screen, and then they click a computer key as quickly as possible, depending on the color, of course. Each game that they played consisted of 10 targets, and the program would report the mean of these 10 targets. Now, each participant would play the game 10 times, and the mean of these 10 games was the outcome variable used in this study. Now, this game was played 4 times. The 10 targets were all red or all green. Before each game, the student either carried out 10 minutes of exercise or they did not. Therefore, we have a 2x2 factorial layout of treatments, and you can see this here with your 2 rows, color and exercise. So by color, you have green, these 2, red, these 2, but within green, you'd have no exercise before, yes exercise before, and within red, you'd have no exercise and yes exercise before they would play the game. Okay, let's have a look at the code. But before we get started, I just want to remind you that in this lecture, we're going to show you the analysis of the same data set using 2 different layout of treatments and 3 different allocation of treatments. So in the previous slide, we showed you that the layout was, the actual layout to the study was a 2x2 factorial. In this slide, what I'm showing you is the one-way layout of treatments with a completely randomized design for the allocation of treatments. Now I put here pretend because this is not actually what happened. PROC-GLM, you guys recognize that. Of course, your class variable is group, no surprise. We're using as an outcome the mean of 10 games. Here is your group variable once again as an independent predictor. I'm here specifying I'm only interested in the sums of squares type 3 to be displayed. If you remember a few slides back, I said pay attention. You should only be looking at type 3 sums of squares in your ANOVA output. Least square means, of course, we're asking for the t-test comparison between groups as well to compare. Okay, here's our output. All of this is going to start to look a little familiar to you just because we've been analyzing the same data set quite a few times now. But if you look at your R-square, once again, remember the R-square represents the percentage or the amount of variability in your dependent variable that is accounted for by your model. In this case, it's about 6%, so 5.9%, which is very low. So that means that your model is really not a good fit. It's shown here by the p-value for your model, which is not significant. If you look at your mean, the mean of your outcome is this is your reaction time is going to be 0.3. Down here, when we look at the variable for group, so the independent predictor variable group is not significant at 0.13. So on this slide, we're looking at the least square means, and we're asking for the least square means in order to look at pairwise comparisons between all of the layout of treatment. So in this case, there's color and there's exercise. In this case, I'm choosing to look at when the group 3 and 4, I can tell you because this is the way the data was coded, this is no exercise between red and green. So that's what 3 and 4 is. And so I'm looking for the comparison between red and green reaction times when no exercise was applied. And my hypothesis is if you didn't exercise, you're fresh, you're rested, and so your reaction time is going to be snappy and much better. And that's the reason why I'm looking at these two groups. Now, just as a note, the difference between your reaction times here is 0.335 minus 0.301, which gives you a difference of 0.0342. So just hang on to that difference. Okay, so the second part of the least square means output, you can see here that the difference between the means 3 and 4 is 0.034252, which we just did in the previous slide. This is the confidence limits of the difference. And just I'm adding here as a note that the p-value for this, which was on the previous slide, is 0.0598. So it's just not significant. You're like, oh, that's a bummer. But before I get too carried away here, don't forget that the p-value for the parameter estimate of the group variable 2 slides ago was p equals 0.1313. So it was not significant. So I just want to bring that to your attention that be careful when you're looking at the overall difference for your group variable, which would mean any significant difference between any of the 4 levels, which is red or green, with or without exercise, and the overall p-value said no, there was no significant difference. So this is why we say here, to ensure overall protection level, only probabilities associated with pre-planned comparisons should be used. So if by hypothesis you were looking for this comparison of 3 and 4, then you can continue on. If you are not, if you were interested in all the comparisons, then you should have stopped when you found that no significance was found for the group variable. All right, how about now we do the same allocation and treatments as a completely randomized design. However, the treatment layout is now a 2x2 factorial. So in this case, you'll see that the code looks very similar. However, we now have as a class statements color and exercise. So we don't just have a single group variable that incorporates the 4 different combinations. We now have 2 class variables, one for color, one for exercise. These, of course, are included as independent variables in your model. And don't forget, we want to look and see if there's an interaction term, a significant interaction term, which means that there could be differences between the 4 different combinations. Once again, we ask for our LS means, in this case, for color on its own, for exercise on its own, and for the interaction. Once again, let's look at the ANOVA output for this completely randomized design with a 2x2 factorial layout. Once again, we're going to look at the overall R square, and you'll see here that, oh, it's still the same, about 6%, which is terrible. The mean's the same. The p-value for your model has not changed. When you come down to your variables, independent variables in your model, you have color, exercise, and the interaction. The one you're going to want to look at is the interaction. That's the one where if you have an interaction term in your model, you're going to want to see if it's significant or not, because that will allow you to proceed to the next levels of your analysis, where you're looking at paired comparisons between your groups. And in this case, sorry, it is not significant. Not a surprise, considering the previous analysis we did. With the least square means, once again, we're making a comparison between, you see here, it's easier to identify what we're looking at because we now have both variables in the model. So you'll see here for color, green and red, and exercise, yes and no, that the one we're interested in looking at is 3 and 1, which is red, no, and green, no. That's what we were looking at, and that's our hypothesis. And you can see, oh, it hasn't changed. It's still not significant. Same deal, same difference, same confidence limits. Now SAS throws in this useful figure for you that gives you a visual of the differences between the means by the combination of your groups, which is your interaction term. By the way, there's a visual representation of your interaction term. Now in this one, we're changing the allocation of treatment. So now we're using a randomized block design with a one-way layout of treatments. So here you'll note that we're back to this group statement, right, which has the 4 different combinations, but this time we're adding ID, which is your participant. Each participant is going to be a block, and the reason for that is because we're assuming that the participant is providing reaction times for each different combination. So with this randomized block design and a one-way layout of the treatments, let's have a quick peek at the R-square, and oh, it's looking much better. So now we're looking at 85%. So we're accounting for 85% of the variability in your dependent variable, which is your reaction time, by the model, which is now very significant. If you look at your group variable, which is your 4 combinations of exercise and color, you'll see that it is significant. So this would be a green light, go forward to have a look at the pairwise comparisons and the t-test. Okay, looking at the least square means again. In this case, we're back to the numbering of 1, 2, 3, 4 because we're using the group variable. As you know, the ones we're interested in is group 3 and 4, which is red, no exercise, green, no exercise. Down here, we're looking at the matrix of the comparison, the paired-wise comparisons between the groups. This is a t-test, of course, testing against the null hypothesis that there's 0 difference. The probability here expressed is of obtaining a t-statistic, one the same or greater than the one that we obtained. In this case, for 3 and 4, the comparison, it is significant. If you look over here, which is the least square means confidence difference and their confidence limits, once again, same difference, same confidence limit. It is now very significant. Just out of interest, I've copied over the p-values just from this table to make it easier for you. And you can see there's 2 others that are significant and 3 that are not significant out of all the different combinations. Because we had an overall p-value that was significant for the group variable in the previous slide that we saw, that means that it opens the door for us to check all of these various combinations to see which ones are significant and which ones are not. So if we're having a look at all of these various pairwise comparisons between the levels of our group variable, as you know, I'm sure you've all heard of this problem of multiple comparisons, that if the more comparisons you're doing, the higher the probability you could find a significant difference just by chance alone. And so in order to avoid that, we do what's called a Tukey adjustment to the p-value in order to account for those multiple comparisons. And so this is just an option in your code that you say adjust equals Tukeys, and what it does is it performs the Tukey adjustment for the p-value. When you do that here, you'll see that, for instance, for our comparison of interest 3 and 4, that the p-value is actually a little bigger. It's still significant, but it's a little bigger. Same applies for the other 2 that were significant. They remain significant, but the p-value is a little bit bigger. No change essentially for the other 3 because they're just even more not significant. So that's when you would apply a Tukey correction, is when you're interested in looking at all the possible comparisons within the levels of your group. Okay, finally we get to the allocation of treatments as a randomized block design, which we just saw, but this time with the 2 by 2 factorial layout of the treatments, which is actually what happened in our study. So as you can see in terms of code, not a big surprise. The only difference here is instead of the group variable, we're using the color and exercise variables, each separately. And we're including, of course, the ID, which identifies the patient, or sorry, the subject, who is considered a block in this design because they're participating in all of the combinations, all the possible combinations, and then we're going to compare within each block. Okay, when we have a look at the output for this final analysis, we see once again the R-square, fantastic, 85%. The mean hasn't changed, of course. The model probability is still significant. Of course, nothing's changed there. But what's interesting here to look at is the interaction term between color and exercise. If you remember last time we did it, it was not significant. This time it is close to significance. So 0.0540 is quite close to significance. So that's very reassuring. Would it mean that it's perfect? No, it would be perfect if it was completely significant. But in this case, it's definitely worth moving forward and looking at the paired-wise comparisons. Now in the least squares means, we asked for please compare color and compare exercise separately, and so that's what it's done. And so when you just compare color, you see that there is a significant difference between color. So the difference is 0.0228. Here's your confidence limit. And when you compare exercise on its own, so just yes exercise, no exercise, you also get a significant difference between the means, and here is the confidence limit, which of course does not include 0. When looking at the least squares means for interaction, once again, you can see in the 2 by 2 factorial layout, we have the two variables of interest, grouping variables, if you wish, of interest, color and exercise, are now apparent. When we want to compare no red versus no green, it's down here, 3-1. Once again, of course, it's significant. No surprise, because we already saw this with the same block design, but with a one-way layout. And then here's your confidence limit, which of course does not include 0 because it is significant. This is the nice visual representation of your interaction. And when we adjust for two keys, we get the same p-value of 0.005. As we did before in the one-way layout. So you're going to be saying, well, why did you go through all this and show us all these different combinations? Well, the reason I'm doing this is just so that you get an appreciation that depending on how your study is designed, there is an appropriate analysis that is coupled with it. And if you don't use the correct analysis for the design of the study, there is the chance you are going to get wrong results. And so this is just a way of showing you that for the same data, there's multiple ways you can analyze it and get slightly different results, or actually grossly different results that you need to be aware of. And you can walk through this slowly and just in the future and just kind of get a handle of what was done. But that's the reason we wanted to show you this, was to make you aware that you definitely need to couple together the correct analysis with your study design, actually what was performed in the study. So I made a comment in the previous slide about the one-way layout of treatment versus the 2 by 2 factorial layout of treatment, where that when you had the 2 by 2 factorial, you had the two grouping variables of interest that are in your model. And that would mean that the subjects were randomized to both color and exercise, and they perform those 4 different combinations in a random order. So that's the 2 by 2 factorial design, but it's convenient because you have the two variables in the model. And here's another example of why it's important to consider those grouping variables in your model separately. Suppose in a study that compared two drugs, A and B, that drug A had better results, but a greater proportion of males were in the drug A group than in the drug B group. And the drug A group had a younger mean age than in the drug B group. And finally, a smaller mean weight in the drug A group than in the drug B group. So you're going to say, well, so who cares, right? So you should care if one or more of these variables are predictive of the outcome, which is often the case, right? Weight, age, right? Male, female. Now, a variable that is a predictor of the outcome and unevenly represented in the two groups is called a confounder. And if it's not included in the statistical analysis, will lead to biased results. So this leads us back to this advantage of using the GLM procedure as compared to the t-test. And you can see here, I've highlighted in red the difference, right? So if you only include the group variable, then you're essentially doing a t-test. And we've shown that if you run PROC-GLM with just a single group variable, you get the same results as doing a t-test. But in this case, researchers can include variables such as sex, age, height, and weight in the analysis and use PROC-GLM. And this is going to be much more powerful for you in terms of analysis because you can take into account the differences in balance between these groups and their relationship with the outcome. Okay, let's try and express this in words. So suppose the p-value associated with comparing the two means was 0.001. So you're happy, but the critics ask, were the groups comparable? And what do they mean when they ask this question? So you're going to say, I compared them, didn't I? Isn't the p-value less than 0.05? Sure. But with that observed difference, I can rule out chance as the explanation for the difference. Now, I might be wrong, but the smaller the p-value, the stronger I feel about my conclusion. So even if there was a balance of these other predictors, as we just said in the previous slide, that we should account for these variables because they may be out of balance and associated with the outcome, they would be included in the analysis. Well, we keep them in the analysis because they would explain away some of the residual variation and make the p-value associated with the drug effect smaller. So that's the importance of including confounders in the analysis, regardless of how strong a confounder it is, because it actually will explain away some of the residual variation. And then here's your warning. Even then, I may have been fooled by randomness. So we never know for sure, right? And that's something to keep in mind. And there is this wonderful book called Fooled by Randomness, The Hidden Role of Chance in Life and in the Markets, that maybe you should read. It's quite a good book to read, and it gives you a kind of a flavor of this randomness that we're talking about. Okay, let's sum up a little bit of what we've been talking about. Step 1, determine the p-value for the exposure variable. In this case, it was drug. In step 2, determine whether variables such as age and height are predictors of the outcome variable. In this case, it was FVC. If so, then including them in the data analysis will reduce the sampling variation and lower the p-value. That's always a good thing. Finally, in step 3, if in addition such predictor variables are unevenly represented in the two drug groups, they are called confounders. And the drug effect may be biased, and correctly including them in the analysis may increase or decrease the estimated drug effect. Okay, so that brings us to the end of lecture 2 from part 2. And in part 3, in the first lecture, inevitably, we are going to talk about confounding.